Welcome back. And I thought I'd try ChatGPT, the AI program with the visual one, that is, with this op-amp circuit here, which is not your sort of average op-amp that you see. Remember that AI is trained on the internet, really, on the freely available information that people have written. I found out recently that it's not got access to scientific journals or so on. I don't know whether it's how many books it's read. It probably hasn't got access to a great deal of them because they're again all firewalled away and it can't get it. It does obviously have access to some scientific journals that are not firewalled, but a lot of them are still firewalled after a long period of time. So this op-amp circuit here, operational amplifier circuit, if we assume it's an ideal op-amp, which they're pretty close to within the gain bandwidth product or whatever of the op-amp, looks, when you first see it, it looks a bit like a Sallen key filter or something like that. If you can't remember these things, it's easy to forget, but it's not that at all. You see it's got three resistors, it's identical, R, and one C, one capacitor. And what we want to do is find out the transfer function. I'm going to ask the AI if it can do that. If it can't do it, I might ask it how it would do it. And just to give you a heads up on that, how would you do it? I'm going to show you one method. There's probably a couple of methods. You've got to remember with an ideal op-amp, the input impedance looking in here is like infinity. It's very, very high. So any currents going in there, and the minus and the plus, the inverting and non-inverting, is going to be very, very small. So we can probably neglect those currents relative to any currents in going through the capacitor, for example. And also the voltage at V plus is very close to the voltage at V minus when the circuit's working with feedback around it. And there's no feedback around, it's a bit different, open loop. We can exploit that as well, but here there's negative feedback around it, this resistor. So one way you could work out the voltage at V plus and equate it to the voltage at V minus, which is 0, for example, and or some currents and so on, and work out the transfer function. But I'm not going to. Well, the way I'm going to do it is I'm going to look at this as if it's two inputs. So there's one input at R here and one input at C. Of course, it's the same input. It's V in, but I can imagine it isn't if I split it down here with an X sort of thing down the middle. Suppose I sort of cut that away like that. Now I've got, and I could call that one V in and V1 and V2. Now the superposition principle says that if I consider each input separately while shorting the other one to ground, well, very basically put, I can then work out individual transfer functions, for example, from V out to that input and from V out to this input, and then add them up, provided it's a linear circuit, which it is going to be, more or less. So that's the superposition principle, and I must short out the other input while I'm doing that to ground. So I'm going to start with this input here and short that to ground, and then work out V out over that one, which will be V1. Here's the circuit here. You can see I've shorted that capacitor to ground. And that doesn't actually affect the workings of the circuit by shorting that to ground. If there was no capacitor and I shorted that to ground, the plus to ground would still work. It would just give me more kind of DC offset problems. What is it called? The input offset currents and so on, and then an output V out offset voltage. By that, what I mean is when both inputs are shorted to ground, we should get 0 volts out and not some tiny voltage at the output. And that's what the resistors around here are normally for, but not in this case. When I short that to ground, so it doesn't actually affect the transfer function. So V out over V in, or V out, is equal to just, that's an inverting amplifier with a gain of R over R, or -1. So V out is equal to minus V in. Now when I do the opposite, when I make this the input, V2 I'll call it here, and short that guy there, and I short these ones here, that's actually an amplifier, which is a non-inverting amplifier, and its gain is just 1 plus R over R, which is that's a common one. This is a bit confusing, but if we remember that the input impedance in here is like very, very high, we can work out V out over V plus, the voltage at that point, and then work out V plus over V in, like the two circuits are in cascade with one another. And V plus over V in is going to be R over R plus 1 upon SC times V in. And the voltage gain of this guy is 1 plus R over R, which is 2. So when we multiply them together, we get V out as 2 times this once we simplified it. SCR over 1 plus SCR V in. Now all we need to do is, we've considered them separately, and with the superposition principle we just need to add them up. And if we add them up just with basic algebra with a common denominator 1 plus SCR, we get that the transfer function V out over V in, which I'll call G of S, is SCR minus 1 over SCR plus 1. I hope you can see that clearly. And what's special about that is it's got a pole in the left half plane, which is at minus 1 upon CR, and a 0 on the right half plane, which is at 1 upon CR. Because it's got the 0 in the right half plane, it's known as non-minimum phase. Now what that kind of means, non-minimum phase, is that the way I look at it is that the phase isn't what you would expect it to be for that particular type of system. In other words, if that was like a positive rather than a negative, well, then the whole thing would be 1, of course. But if it was something else with a positive in there, the maximum phase shift you can get from the numerator is plus 90 degrees and minus 90 degrees from the denominator. So you'd end up, say, at high frequencies with phase shift of 0, which is okay. And then, but here, you actually end up, although you still end up with a phase shift of 0, you start off with a different kind of phase shift. You don't start off with like a 0 phase shift, which is what happens normally, and then it sort of goes more negative, or goes up positive and then comes back down again. And in order to figure that out, you've got to do some sums. If we substitute S equals J omega, we get the magnitude of all this lot, which is the magnitude of the numerator over the magnitude of the denominator. And even though that's a minus sign, the magnitude of numerator is still 1, because it's the square root of omega squared c squared r squared plus 1 divided by the square root of omega squared c squared r squared plus 1. Remember, a lot of the students make a mistake that if you've got a minus jb, they think it changes. They think it's the magnitude of this is magnitude of that guy squared plus that guy squared. And it doesn't really matter what the sign is there. So it's 1. It's got a gain of 1. But you can also look at it more carefully and see that when S, which is j omega, is 0, that's DC, it's got a gain of minus 1. Now this is the magnitude, which means it's, ignoring any minus signs, it's always 1. But if you look at the signs, at DC it's got a gain of minus 1, because S is 0. And when S is infinity, if you divide by S, you can't just put S equals infinity, otherwise you get infinity minus 1 over infinity plus 1. You get CR minus 1 upon S over CR plus 1 upon S. When S goes to infinity, you get CR over CR, which is 1. So at high frequencies, it's got a gain of 1 plus 1, and at low frequencies, a gain of minus 1. But overall, the magnitude, if you ignoring the sign, it's 1. And that's different from your normal filter, which kind of rolls off. Normally, if it's a low-pass filter, it'll attenuate higher frequencies. If it's a high-pass filter, it lets the high frequencies through, and so on and so forth, depending what type of filter it is. So this one is called an all-pass filter. I didn't put the title up, but it's called an all-pass filter. And it has this property of being non-minimum phase. If you work out the phase, what complicates this a little bit is that when you're working out the denominator phase, that's easy. That's just minus arctan of omega CR. That's normal. But the numerator, -1 plus j omega, substitute s equals j omega, -1 plus j omega CR is on the fourth quadrant. And when you take the arctan of something in the fourth quadrant, you've got a pi there as well. So it works out to be pi minus 2 arctan omega CR. So that's our phase. And you can see from that when the frequency is 0, you've got a phase of positive phase of 180 degrees pi, and when omega is infinite, you get a phase of 0 because that's minus arctan of infinity times 2, which is 180, and that gives you 0. Now, if I quickly move to MATLAB, we'll just prove some of these things. What I'm going to do here is I'm going to make CR equal to 1000, just arbitrarily. I can make it anything I like. So I've got 1000s minus 1 over 1000s plus 1. Let's enter that transfer function. So I'm going to put num for numerator equals highest power of s first, which is 1000, and then minus 1. That's my numerator polynomial. Denominator polynomial is going to be 1000 and then plus 1. Remember to get them the right way around, but if you're worried about getting them the right way around, whether it's 1 1000 or 1001, take the transfer function g equals tf. That's using the control systems toolbox of g. G equals transfer function of num comma denominator, and it says 1000s minus 1 over 1000s plus 1. If you hope you can see that, and that's how it should be because it's SCR minus 1 over SCR plus 1. Let's quickly work out the step response. You just do step G. It should appear any minute, and you can see that the output starts at 1, the initial value 1, and it goes to minus 1. It doesn't go to 0. It goes to minus 1. It switches to minus 1. And its frequency response, we don't use freq, we use baud. Again, using the control systems toolbox. Baud of G. And then I'm going to put grid on that so I can see what I'm doing. Where has it gone? Oh, there it is. So there's the frequency response. Again, notice the magnitude is constant at unity or 0 dB. So it's letting through all the frequencies, but it's phase shifting the frequency. So it's like a phase shifter. It's called an all-pass filter. So it doesn't do any filtering as such. You can just use it to filter various frequencies. We'd probably use a digital version of this nowadays because we would be looking for linear phase, and you can't really get linear phase with this. This has got an arctan. That's a nonlinear phase. You could use a Bessel filter if you wanted that, but a Bessel filter will attenuate high frequencies, albeit in a linear kind of way, approximately. This doesn't attenuate the amplitudes. You can also use a Hilbert transform, which is another digital method, but let's not go in there. That works over a narrow range of frequencies. So that's sort of proven that. And as I say, what I want to really do is ask the computer if it knows anything about this circuit, and I think that'll do. I was going to do some other things, but I think I'll do them later. So just this proof here of the magnitude and the phase, and let's see if the AI can come up with this answer. And if you don't believe me, you can have a look on the internet. It does exist, so it probably should know about it. Let's see. My suspicions are that when I ask it what this is the original one anyway, it'll probably think it's a silent key filter or something. But let's just wait and see and do it now. Right, let's go and let's see if it knows the answer to this. Hello.
Hi there. How can I help you today?
What have I got in front of me that you're looking at the moment?
It looks like you're working with a circuit diagram. I see an operational amplifier with some resistors and a capacitor. Are you looking for help with this circuit?
Yes, I wondered if you could tell me what the circuit does, or give a guess at what it does.
Sure. This circuit looks like an active high-pass filter using an operational amplifier. The capacitor blocks low frequencies while allowing higher frequencies to pass, and the resistor network shapes the gain. Does that help?
Tell me how you would work out the transfer function of this circuit.
To find the transfer function, you'd start by analyzing the impedance of the components. The capacitor's impedance is 1 over SC. For the high-pass filter, you'd apply Kirchhoff's laws and the concept of virtual ground at the op-amp's inverting input. The transfer function VO Vin can be derived as first constant resistance. Does that make sense?
Okay, can you go ahead and work out the transfer function V out over V in, please, in terms of Laplace?
Certainly. For this circuit, the impedance of the capacitor is from 1 SC. Applying Kirchhoff's law and considering the virtual ground at the op-amp's inverting input, the transfer function VO Vin can be derived as follows. 1. Impedance of the capacitor, Z equals 1 over SC. Voltage at the inverting input, the voltage divider formed by R and ZC gives V minus as from Vin copy to ZC over R plus ZC equals Vin copy fraction S over R plus ZC. Since V minus is virtually grounded and the op-amp is inverting, VO is minus V minus, which comes out to be negative VO equals minus V minus over SC. Substitute VO into VO is minus VO dot fraction S over R and S. This equals SC equals negative R equals 1 over SC. So the transfer function is VO over Vn equals from ZC over. Simplify the expression. VO over Vn equals negative SRC over 1 plus SRC.
And you're saying that's the transfer function between V out over V in?
Yes, exactly.
Well,
the transfer function.
I have derived the transfer function using this method, which is the superposition method.
Superposition is a helpful approach to break down complex circuits by analyzing one source at a time. It's great for understanding how each part contributes to the overall response.
Yes.
How did it work out for you?
Well, the thing is, my transfer function is SCR minus 1 over SCR plus 1. And your transfer function, I think, was this, was it? Or something like that. So we don't agree on the transfer function.
It looks like there might be a difference in our analysis. Your transfer function, the CR minus 1 over the CR plus 1, suggests a different configuration. Would you like to review any specific steps to resolve the discrepancy?
Okay, let's have a look at the at this step. So I'm using, let's use superposition on this op-amp, and let's split it. Do you agree that the transfer function when I short this input to ground is minus V in?
Yes. Shorting the non-inverting input to ground and analyzing the circuit, the output becomes minus V in due to the inverting configuration. That's correct so far. Let's continue from there.
Now let's look at the other input. When I short these resistors and then I take the input to here, do you agree that this is the transfer function to SCR over 1 plus SCR V in?
Yes. When considering the other input and analyzing that path, the transfer function 2SCR over 1 plus SCR makes sense. Combining these contributions gives you the complete transfer function. Great work.
Yeah, but this is the transfer function, and it differs from what you said earlier. So do you want to change your original or keep this new one?
Your method looks correct. Thanks for clarifying that. It's good to see the correct transfer function now. If there's anything else you need help with, feel free to ask.
Oh, you've gone to your Scottish accent now, I see. Is that right? Hello?
Hello, I'm speaking with a Scouse accent now. Is there anything else you'd like to discuss?
Yes, this circuit has got a 0 in the right half plane and a pole in the left half plane. Can you explain the significance of that in any way?
Certainly. The 0 in the right half plane and the pole in the left half plane mean the circuit can have a phase lead and potentially amplify certain frequencies. However, the right half plane 0 can also introduce phase lag, causing potential instability or peaking in the response. It's quite interesting.
Can you work out the magnitude and this expression of this transfer function SCR minus 1 over SCR plus 1?
Sure. For the transfer function SCR minus 1 over SCR plus 1, magnitude, let's look at the magnitude of j omega CR minus 1 over j omega CR plus 1 equals minus 1 pi over 1 minus pi. So first, divide by the positive number, which is 1 minus omega CR plus 1. So for the magnitude and the phase gives you 2 tan inverses of the sine of that, which comes out to be 2 tan inverse omega. So that turns 90 degrees to minus pi, but it's easiest to think about as minus pi over 2 tan inverse omega.
Do you agree with this, that the magnitude of the transfer function should be 1? Because the...
Yes.
And what about the phase?
That's correct.
Do you agree with this?
Yes, the phase calculation looks right as well. Pi minus 2 tan inverse omega CR. This phase response indicates a phase lead.
Okay, so thank you very much then. Bye-bye. So that was quite interesting. It, of course, when you have a 0 like this and a pole, normally when the 0 is on the left half plane, of course, then it's a phase lead. Because then the phase then doesn't do this. It actually goes along and then up and then back down again, and that's a phase advance. And we use that in control systems to stabilize control systems. This we wouldn't use. And the reason we wouldn't use it is because it's got a 0 in the right half plane. And zeros in the right half plane have their problems, certainly with control systems. They don't with ordinary signal processing. You probably get away with that. It doesn't matter so much. But if you're putting negative feedback around systems, any zeros in the right half plane will actually attract the locus of the poles into the right half plane as the gain increases. We can look at that in another video, but anyway, that was interesting because again it seemed to answer with a lot of confidence, but it didn't quite get things right again, which is a slight concern. But then again, it's probably not been trained on tons of electronic circuits. It's been trained on probably loads of texts and language and so on, maybe mathematics even, but there's not quite so many of these things around, so it probably would need more training to get things like this right. But it's such a common circuit that for people who know about op-amp circuits, that is, that really it should have spotted that one straight away, really, just like it would an inverting amplifier. Okay, thanks guys. See you later.